Hello, ladies and gentlemen. So, coming back from the problem you guys are supposed to do, here's a MATLAB output showing the response. So, that ends our discussion of first order equations. Moving on to second order equations. So, we got two different types of circuits. One is where all the elements are in parallel, and one is where all the elements are in series. And we have a voltage source for the ones in series and a current source for the ones in parallel. Now by KCL, the sums of all these currents have to sum to zero. By KVL, the sums of all these voltages have to sum to zero. So let's go look through that. We have the equation for KCL, and we write down all the current equations for the three different elements, for the resistor, for the inductor, and for the capacitor. And then we just plug them in to the KCL equation above. And we get this differential equation. It's got an integral here and a derivative here. We just differentiate both sides of it. So we've got C d squared v dt squared 1 over r dv dt and 1 over L V equals the derivative of this side. This is a constant. It's the current flowing at time at the original time. It's a constant. The derivative will be equal to 0. Next, KVL, similar. The sums of the voltages have to be equal to 0. We write down the three voltages across the three elements. Plug them into that equation. We get integral equation. Resistance times current will equal the voltage. The integral of current divided by capacitance equals the voltage plus whatever voltage started on the capacitor. And then the inductance times di dt is the voltage across the inductor equals whatever we're forcing. Differentiating both sides, L d squared I dt squared, R di dt, and then I over C. It has to equal dvs dt, and the derivative of this is a constant. It's the voltage across the capacitor at the original time. Derivative is going to be 0. So we got two equations. This equation and this one. This one for this circuit. This equation for this circuit. Okay. We're going to consider this. So here's the two equations. We're going to consider the case where we have constant current source or constant voltage source. Dis dt is going to equal 0. So it's those former equations set equal to 0. Instead of this, it's going to be set to 0. Same thing when we're dealing with a voltage source. We get this equation when the voltage, in this case, the voltage is a constant, or in this case where the current's constant. Now, you'll notice we have coefficients of C, 1 over R, and 1 over L here, and we have the coefficients of L, R, and 1 over C here. So we standardize the equation. We put it in a form we can deal with. We divide through, in this case, we divide through the whole thing by C. So this middle one will become 1 over RC, and the end one will become 1 over LC. And this will become R over L here and 1 over LC here. A1 and A2. A2. Okay. Now, we're going to find a particular solution. XP solves this. XP solves that equation. Okay. XC is the complementary solution. XC solves this. XP, the particular solution, plus XC is also going to solve this equation. That's the trick. We have to find one XP and then a family of XCs. Well, if F is a constant, like we considered before, it's pretty easy to see here's a particular solution. Because the derivative of this is 0, we're just going to have A2 times capital A over A2 equals A. Yeah, you got it. Here's the derivatives. Here's the derivatives equals 0. Right there. This then will be a solution to this. Now we're going to revise the equations a little bit. We're going to consider these constants now. Instead of A1 and A2, we're going to talk about this. Omegas are a frequency, an angular frequency in radians per second. And this is a damping ratio. And you get this thing called a characteristic equation. The trick is you want to find the roots of this characteristic equation. Remembering the solutions to the quadratic equation. This is a quadratic equation. You get minus b 2 zeta omega n. There we go. Zeta omega n minus b plus or minus the square root of b squared, which is 2 zeta omega n squared minus 4 AC, well, AC, well, C is omega n squared. All divided by 2. And those are the roots of the quadratic equation. You can re-express this. I'm doing things a little differently than the book, by the way, than the slides and the book. I'm going to call these roots 1 and 2. Where this is a positive sign, it's R1, and there, ampersand sign, negative sign is R2. You can rewrite this equation, this differential equation, as d dt minus R1 times d dt minus R2 acting upon x equals 0. Now you can see why this works, because if this first order equation equals 0, then x will satisfy the solution. If this times x, this part times x equals 0, then it will also satisfy the solution. And now you can see where we get the quadratic equation from. This characteristic equation. Instead of differentials like this, they replace it with the letter s. And we solve for s. We're finding the roots of this equation.